Uh, Good morning. Sorry, hold on one second. Good morning, good afternoon, good night, everybody. Welcome to the February edition of the IREE community meeting. Today we have Ben and Scott presenting about parameters in IREE. And well, with that, I'll hand it over to Ben.
Cool. Yeah, well, there's a bunch of slides here. Post the link in the chat, and I suspect that most of these, if they're not already covered in the documentation that Scott's writing right now, they will be. So I expect this slide deck to go away and just that to be our documentation at some point. We just recently landed parameter support, and I'll walk through what IREE treats as parameters, how we consider them, what our interoperability is with other tools and other frameworks, how to use them in a very basic way, with the documentation and the samples we have being kind of the source of truth on that stuff. And then happy to answer any questions. And I think Scott has like a collab showing some stuff as well, that we can go through. So parameters in IREE are just binary blobs. So unlike parameters in a lot of frameworks that are, pickled Python dictionaries that might contain any kinds of metadata and stuff like that, IREE treats parameters just as binary blobs. Key reason we do this is IREE's infrastructure then doesn't need to take an opinion about what a parameter is or what you're allowed to store in parameters. And as you're thinking of deployment scenarios, what the compiler ingests from a front end now no longer has to be synchronized to what a runtime deployed on device supports. This allows us to kind of very generically treat parameter data through the whole pipeline. And the only thing you need to care about is that your front end and your compiler version understand how to treat your parameters as you're providing them, and everything else kind of falls out from that. Our basic structure is that we treat parameters and parameter archives as just storage for these blobs of data. They have keys, so it's kind of like an index DB or something like that. It's just key value storage. We have some facilities for allowing you to namespace these storage archives. Traditionally, if you're thinking of an inference or training solution where you're only ever running one model at a time, it's kind of okay to just name parameters whatever they are. But in more sophisticated scenarios where you're potentially linking multiple pipelines together or multiple stages of a model together, where you might have naming conflicts, there's reasons to be able to split those apart. The design of the parameters and how we treat them is driven by the needs of them at runtime. So they are optimized for efficient gathers and scatters of parameters into buffers in device memory, optimized for DNA transfers of those. So whether the parameters might be loaded over RDMA or some direct SSD to device memory mechanism, everything is kind of designed to make that efficient. We do support other modes, and I'll get into that a little bit for ones where that's not necessary, but we really wanted to push for something that could support all the high performance paths that everyone is currently pushing on, and then fall back for where we don't. And kind of the thing to keep in mind with parameters as a concept is they're not just a double-edged sword, they're a sword made of swords, and there's only really one way to handle them safely. If what you care about is high performance, low memory usage, optimal behavior on device as you're using them. And it's very easy to fall off those paths. And so in most ML frameworks, this just happens and it's just a fact of life. Because we allow for those optimal paths, it means there's ways to get off of them. Worst case, you end up doing what any other ML framework does. And I have some examples of that. So this is a diagram Scott has in the docs. So basically, if you're today thinking of what IREE produces as a VMFB file on the top there that has both the program artifacts, host and device code, inline read-only data that's been kind of baked in, and then any resources that were originally in your MLIR file that you provided to IREE from your front end, it's all embedded in there. That's still totally good, and in a lot of cases the best deployment mechanism because you have a single hermetic file. the compiler has the greatest opportunity to optimize both the storage of those resources and do any kind of constant expression evaluation on those. So you're going to end up with the minimum amount of memory used at runtime, the smallest deployable artifacts, and the easiest deployment story. There are reasons to use parameters though, and so we support those now. And basically the only thing that changes is some resources, and this can be mixed. It doesn't mean all large resources, like in this diagram here, have to go in parameters. You can have some that are embedded, things that will never change. You can embed right in the VMFB versus things you might want to substitute at runtime, new weights you want to be able to download to an existing model architecture and use. You can now have those reference these external parameters. And it's a pluggable mechanism such that here we're showing IRPA file. I'll get into that. That's our IREE parameter archive, or a safe tensors file, or a GGUF file, or a C implementation of a vtable that you can do anything you want. So if you have parameters already in device memory because you're some JIT framework and you've literally got a CUDA buffer sitting in memory of your parameters, you can now reference those and pull those in. Speaking of references, the way in the compiler, we kind of name these, and these are what you'll see today. There's potential stuff we need to do to get like an IREE input dialect version of these, which make it easier to target. But today, this is kind of the concrete thing. Basically, parameters have a name and they have a type, and that type is a tensor type in the compiler. Again, at runtime, these are just binary blobs, some bite size slab of things. But in the compiler, we use their types. They don't have to be tensors. They're any serializable value. So they could be an I32. Please don't do that, but you could do that. They could be a util buffer, which is just a host buffer. So anything that you could put in a binary blob, like you could put a JPEG in a host blob in here and load it and read it. Doesn't have to be a tensor, doesn't have to be consumed as tensors. It's just a binary blob. And then, as mentioned before, we have a way to scope these with a namespace, and that's really just a way to disambiguate. The safest thing to do, if you can give something a namespace, is give it a namespace, because then it's just easier to debug and diagnose and stuff. But it's okay to use the kind of global namespace if you want. And this is what those look like in a program. So traditionally, if you have embedded resources, you'd have a util global of a constant. So a dense constant, or a resource reference, like an MLAR dense resource reference. But now they can also be these named parameters. And because we have the type and they are serializable values, everything the compiler could do if it was a constant, besides constant expression and stuff like that. But you can load them, you can store to them. Still some work to do on that. But basically, it's just if you have a model and you're exporting it with some globals, ML program global of your constant value, you can replace them with a reference here. And once you do that, so now you've got a program compiled. This will compile down. The VMFB that you get will be referencing these named parameters, and it'll have the code to go load those at runtime. For the tools, the command line tools that we have, there's now a parameters flag. You can pass multiple of these. And here you can see it's passing, in this case, a scope of A, namespace of A, and here's the file to contain those, and a namespace of B, and here's the file to contain those. And the files can be different formats. So in this case, it's loading an IREE parameter archive for A and a GGUF for B. You can also combine files together. So if you do have a sharded set of parameter files, like TensorFlow likes to do the 0 of 10, 1 of 10, 2 of 10 kind of thing. You can pass all of those files. The runtime will combine those into a single unified index and allow you to access those. Pros and cons, and when you would want to use parameters, like biggest pro, especially for developers on the compiler, is that it speeds up your compilation a lot. If you have a 10 gigabyte MLAR BC file, no matter how fast that is to parse, it's still going to be expensive to parse. And writing out a 10 gigabyte VMFB is also expensive. So if you want very fast iteration and you don't care, like the cons and caveats that come along with using parameters aren't relevant to what you're experimenting with, it's a great way to speed up your compilation. That can be useful for users as well. If you're in a more online, eager JIT scenario, you can produce a 1 megabyte MLA-RBC file for your entire model, compile that through into a VMFB, and then you just have your gigabytes of parameters in memory that you might need. The deployment scenario where you would actually want to use parameters are when you want runtime substitution of these. So again, that's runtime substitution of all of the parameters and weights in your model, or it might be if you've got personalization weights, like the last layer in the model might have something that is per person where everything else is uniform. You can do that, and that's why we support a mix of these. You don't have to have everything in parameters or everything embedded in the model. And if you're able to stick with the same model architecture, that means you can perform training and then redeploy without having to recompile or redeploy the model, especially if you're doing kind of the optimal deployment of IREE on embedded systems. You can compile the model to C with a MIT-C, statically link all of your executables in to your APK, JNI blob, or your firmware or whatever. And the only thing you then get out of band are the parameter files. And then kind of the other thing that is common in ML is if you've got a Hugging Face API key, you could just go fetch weights from them and use those. So we support safe tensors for that reason. Of if you just want to use existing weights, someone else is providing those weights, you can get those. The disadvantages of parameters is that as you're doing this, it disables optimizations that we would otherwise be able to perform. And some of these are very critical if what you care about is the actual end-to-end latency of your program, the startup time of your program, or in most cases, the most critical thing is the peak memory consumption of your program. So if we in the compiler can no longer see and interact with your parameters because they're an external blob we don't know about at the time of compilation, it means that if what we need in the compiler is to transpose the right-hand side of a matrix multiply to transpose the weights, whereas we could have done that in the compiler and baked out the transposed version into the VMFB file, memory mapped it at runtime and directly consumed it. Now instead, we have to load the original untransposed one into memory, which we can still memory map, but then we need to allocate something of the same size to transpose into to then consume for other things. And so if you've got 10 gigabytes of weights and we're able to optimize those and bake them out, that could use 0 megabytes at runtime if we're able to map them. And otherwise, it might use 10 gigabytes at runtime. There's some work for that. I have a future work section of what we'll be able to do with the compiler, where we will be able to spit out a module that allows you to perform a parameter optimization pass. So anything the compiler does today, as we do those kind of big constant expression evaluation things, we can spit out a dedicated module that does that. And then at deployment time, whether before you upload these, so as part of your deployment workflow, you run that program, produces the baked parameter archive, you upload that, that's what users fetch, or you download on your bots or servers or whatever, and you get it pretty much as if the compiler had seen it all. Or if your end user deployment at install time on the end user device, you can do the same thing. So you would run the module, produce the weights, write them off to disk, and then future invocations that you do, you would use the ones you produce. So still some work to do there, but roughly that's what we're tracking for that. That will also let us do some interesting things with device-specific optimizations. So data tiling and stuff in particular, we'll be able to optimize on device as part of that flow. Of course, that's more complex, but that's kind of what you get when you do this. Other big caveat for particularly like memory use and stuff like that is that certain file formats that we do accept, like safe tensors, are hostile to anything but CUDA. And so if you're on a CPU or an integrated GPU, they are very proud of not aligning the contents of their files. I don't know why, but that basically means we can't use them. And so if there's 10 gigs of weights aligned at 1 byte alignment in their file, which it is, we will have to wire all of that memory, load them into memory, so that we can ensure 64-byte alignment for SIMD and stuff. So just a caveat, you can save a lot of bandwidth getting a safe tensors file, but it doesn't necessarily mean that you're saving on the other side as well. There's also in some cases, anything that we can see in the compiler, just as you can do, expression simplification in a normal program, if you can see all the expressions, we lose the ability to do when we don't know, if you have 1,000 parameters, we can't bucket and bin and collapse or do really anything with those. And so that compared to wiring 10 gigs of memory to transpose something is not too bad, but it is a kind of additional overhead to the system. And depending on your model size and your latency requirements, can matter. And then you also just have to be aware, once you end up in these more complex deployment scenarios, you're now handling multiple files, and it becomes a little bit trickier to version that, but that comes along with the territory. We support a couple formats today. These are mostly just convenience things. So we support GGUF. There's some issues with that as a deployment format because the format is non-hermetic. It requires information about how you compiled and the compiler flags you use to compile GGML in order to interpret the contents of the file. So particularly for the more esoteric quantization schemes, it's not possible from the file itself to even know how to interpret that data. So there's some caveats there, but at least they have good alignment. So if you have a GGUF file, you can use that interchangeably performance-wise with one of our own archives. Safe Tensors has no alignment. It's byte aligned, and you really should not trust the performance of that. You can still use it, and if you've got a 70 gigabyte Safe Tensors file, then you don't want to have to duplicate that. Go for it, but just be aware that that's going to require 70 gigabytes potentially of wired memory to use. And then we have our own format, which is similar to GGUF, but has some additional features for versioning and deployment. And that is the one we support for full read and write. Both GGUF and Safe Tensors, we only read. We can add more formats in the future, but we're trying to keep it simple, small, and pragmatic. We don't want protobuf to be a dependency of the core compiler, but it's very easy to convert these files. And so having Python scripts, for example, that load a PTH file from PyTorch and then produce an IRPA file that then the rest of the tooling can consume is kind of the ideal workflow for that stuff, versus trying to actually parse a PTH file in C. That's real hard. For the kind of big performance things, I just want to get this out of the way. This is the global flag that basically decides how we treat the files. If you're targeting a device with unified memory, where you want to be able to map the files into memory and use them directly, then you want that first flag saying, my memory model is unified. That disables certain optimizations for being able to perform the memory mapping at runtime. So generally, if you're targeting a CPU device or an integrated GPU, that's what you want to do, because we can directly map from the file, bring them into device memory, whether that's CPU or GPU memory, and use them. If you're targeting any traditional discrete GPU or accelerator, then the discrete model is the better one. That allows us to allocate device local memory for all of the parameters to be loaded into. And then we do an efficient gather of all the parameters as they are on disk into that memory. It allows us to bucket the memory, limit memory size requirements for devices that have maximum allocation size. The death by 1,000 paper cuts kind of optimization issues go away because we're able to treat these as nice big slabs of buffers as opposed to 1,000 individual parameters. Kind of there. Today, that's a big global flag. Or you can provide this on the module that you give to IREE with a stream resource config dialect adder that specifies it. There's a step that'll be done for the HAL targets that we have, where HAL targets will be able to say what their memory model is, at least as a default. So, the CUDA target can always say that it is discrete, whereas a CPU would be unified, and then something like Vulkan could be either depending on the devices you're targeting, whether you're targeting integrated devices or devices with discrete memory. Just as the general rules, if you care about kind of the performance at runtime, the memory usage, and kind of the features that you want for deployment and versioning, use our archive files, and definitely not Safe Tensors. GGUF is fine if you have it. If you're on a discrete GPU, then you really want to set the discrete setting on the memory model. And today it defaults to unified just because it is catastrophic to do discrete on CPU, because it prevents us from wiring the memory there. So again, problem with default flags. So if you really care and you know your device, this is a flag you want to be passing to make sure you're controlling that. And then kind of the biggest one from the front end and the design of this is don't put hyperparameters in parameter files. Hyperparameters controlling things like conditionals in the model, things that change the model architecture. The compiler really needs to see those. It's common, I've seen in these things, to have the batch size as a hyperparameter that ends up in a parameter file, and it never changes for the usage of that at runtime, but it means that the compiler is never able to get the hint that the batch size as a dynamic dimension is anything but potentially 1 or a billion. So anything small and constant should still come to the compiler. Parameters are useful for runtime substitutable stuff and things that are really big. As for the extensibility, we have a couple different ways to do it. The easiest one is if you have a file format that is blocks of memory on disk in some way, then you can implement one of these methods under this formats directory. They can be out of tree, they can be anywhere. That basically just given a file path or a file stream, go populate an index with references to the blobs of data. So we have that for safe tensors, gguf in our own format, but you can do anything you want. That is for file-backed parameters. And then we have a provider. Providers are the thing that really take the requests that the compiler produces to gather and scatter parameters and does something with them. The default one that we have today is the parameter index provider, which uses those indices that we build to operate on files on disk. If you want or have the need, you could build your own providers. So examples of that would be when you already have the parameters in memory and you never want to hit the disk, you just want to say, here's my CUDA buffer that contains these parameters in memory, use that. You would just insert a mem copy from that. Or in the case of a load, directly return your buffer 0 copy. Or you could create a caching layer here. So if you wanted to have multiple instantiations of a model all sharing the same parameters in memory, the parameter provider is where you can do that. That's where you would manage your device buffers, and then as different instantiations of the model go to ask for those parameters, instead of allocating new memory to put them in, you can return the same memory. And then finally, today we pretty much just have the couple paths for, I think, just Turbine really. Unless you're doing this by hand. But in input dialects that may have the ability to reference external parameters and stuff can be converted into our parameter references so that we can handle them. The big future work is, as mentioned, the two big things that control performance are like the compiler being able to see the parameters. Oh, I meant to change that to import file. So we have this pass, and I'll talk about it in a second, that lets you, given an MLA-RBC that might have embedded parameters inside of it, to fork them out to an independent file. We basically need the inverse of that pass, that if you have an MLA-RBC referencing external parameters, be able to give the compiler the parameters so that we can bring them back in. Ideally, I think we can do that pretty easily with the parameters of just creating resource references that reference the files on disk. So all the benefits that the compiler gets from that just kind of happen. So it doesn't mean you have to load then 10 gigabytes of parameters directly, but we use the same path. So that needs to be written. That's a pretty easy one. And then the bigger one is the splitting out the const expression evaluation into a dedicated module. So this will likely be a compiler flag you pass that just says, IREE opt parameter optimization module output. Yeah, as long as there's no endian issues in your resources. Yeah, so basically a flag that lets you spit out, in addition to the VMFB the compiler produces, the VMFB that provides the const expression evaluation. And what we'll do there is just yank the initializer code that would exist in the module out and just put that in another module. You then, as the hosting application, are responsible for deciding when you want to run that, whether that's, again, as part of your deployment pipeline before you upload these to a storage bucket, or as an install time action on device, or a runtime cache that you're maintaining as you fetch models over the air and then run them. So the easiest path to get started with this is this pass that was added, that you can pass this flag, and if there's any big constants or resources, this will split them out and replace them with references to the file. Scott and I just discovered there's a issue in here. If there's splats in there, they currently get written as the full output of the splat as opposed to a 4-byte reference. So there's some issues. We'll work through that. This is all still new. But that, if you are compiler developer, someone hands you a 20 gigabyte MLAR file to deal with, do this, get your parameter file out, and then iterate on the 1 megabyte MLAR file that you get out of it. There's also a utility if what you want to do is send someone a reproducer so that you don't have to upload and they don't have to download that massive file. The splat parameter archive export file that creates an archive file that is just splats of the original parameters. So it'll be a couple kilobytes. And that way, if the issue reproduces with that, then that is the best way to send someone a reproducer. If I showed before, you can, for the tooling, pass a -- parameters flag, and our IREE run module, IREE benchmark module, tools like that support that. If you're integrating parameters into your application where you're hosting via the C runtime, this is a basic flow for using the indices. You parse the file, you create a provider using the things you parsed, and then you create a parameters module and add that alongside your other modules as you're creating the context. The Python bindings have some utilities for this as well that kind of wrap this up. But if you're directly integrating against the API, this is what you do. As for creating parameters, we have those passes in the compiler. There's Python API here that as you can see, you give it some NumPy arrays with some keys, and you say go create it. It does the right thing of this will map a file on disk and then go right into the file, so it's fairly efficient. More automatic ways. So this is still kind of work in progress. But if you're using Turbine, then you can use torch parameters and then the magic flag of external equal true on the AOT export parameters, and that should then create a file for you and the module with a reference to those external parameters. Scott, I think, will show a collab of that. If you are creating a conversion tool yourself, or you're integrating into something that does, what that Python code was doing was basically just calling this method. So you can do the same thing. You provide an index saying where to source the parameters from, and then a way to open a file. You let it run, and it will provide you back an index that contains the locations of those parameters in the final file that you reference. So it's pretty easy. This is a more detailed thing that is what that method's doing. Doesn't matter. We have a couple command line tools that are part of the release distribution to make it a little easier to work with these files. So if you want to create a parameters file from thin air, you can use this. IREE create parameters. You can give it data, you can give it splats. All of these tools, by the way, do support flag files. So if you are bash shell script hacking, you can, one line per parameter, create these, pass it, and then spit out a file. And anything more complex, just use the Python API. We have IREE convert parameters, which can convert kind of like a Swiss Army knife. So it can convert parameters. So like the first example is converting save tensors to our archive format, fixing the alignment and dumping the new file. It can also merge parameter files. So if you were to pass multiple parameters flags, it will merge them into one output. It can strip parameters. So with the strip flag, so given a reference input parameter archive that might have full parameters in some format, you pass strip, and then it'll produce one that contains all the same metadata, all the same parameters, but no contents. So good for creating reproducers if what you have is a save tensors file and you just want to send someone the spots. It can also do some additional things. So some parameters are load bearing to correct execution. So for those cases where like the layer loop count is a parameter, which it really shouldn't be, but it is, that stripping that and making it 0 is likely to not give you a very interesting execution profile. So you can substitute specific parameters if they do need to be specific values for hyperparameters. To see what's in one of these files, either one, a GGUF file or save tensors file, or our IRPA files. You can use IREE dump parameters, shows you all the offsets and what's in there and their sizes. You can also extract one or more values from there. So if you want to get the value of a particular parameter, you can give it the name and a file, and it'll dump it to the file for you. And then finally, the API for this stuff, if you want to use parameters, we support loading. So all of these are asynchronous. So they run on device and they run in a timeline along with other work. And so we can load, we can gather, where we take a list of parameters to gather, or we can scatter, where we take a list of parameters to scatter. So these are the core primitives. This is what the compiler targets. And if you're implementing your own provider, these are the three methods that you implement: load, gather, and scatter. And as long as you can follow this API, you get parameters. And that's it. Like I said, most of this, anything from this deck should hopefully be showing up in the parameter documentation. And as we do the additional features like the deployment time optimization and stuff like that, those will get added there as well. Yeah, that's my presentation.
Awesome. I can show a little Colab notebook and then the docs, and then we can probably switch to questions after that. Let's see. Here we go. Okay, so I've got a Colab notebook here using Shark Turbine just to show this export flow. So here I've defined some parameters in my little test module. I'm just doing a little bit of math in this program. And after I set that flag and run through the export flow to save out the MLIR, you can see that they show up as these stream parameter named with the scope and then the keys. I was wondering if there was also a save parameters to get the IRPA file at that point. Skipping past that, what I can do is create parameters from the command line, get a file with some data, and then I can run the program passing that parameter file and get the output that I expect with just inputs, parameters from a file, and no embedded weights in the program. So there are a bunch of different ways that you can hack at your programs, either directly while you're authoring, or if you want to go through the standard compilation flow without parameters and then decide after the fact, oh, I want to turn these things into parameters. Let me run that compiler pass, slice it up differently. And you can choose if you want, oh, I want these Python data with their actual weights dumped to a file, or I'm going to get the weights somewhere else, either safe tensors or just command line. Bunch of different ways to set that up. And then these are the new docs for parameters. They're in the guides section on the website down here. So these are the diagrams that Ben showed at the beginning of that presentation that kind of explain without parameters what your file looks like, with them what it could look like. We have a section on the supported formats. Planning on filling in some of those pros and cons of each format and how to work with them in here, as well as some links to the projects and their references. And then we have kind of a step-by-step how to use each tool with some examples. So if you want to create parameter files, you can use the command line tool, or you can use the Python bindings. You can reference the tests that Stella linked in the chat here to see other concrete tested examples. If you want to convert parameters, these are, I think, just the examples from one of the lit test files lifted up into the docs. I may extract some of these into Colab notebooks that people can run and poke at. For now, they're just text that you can copy paste and update the paths to your own files as you work with them. If you want to inspect the files, you can run the dump parameters tool. And then if you want to load them in with the parameters flag. If few links to the tests that show ways that you can chain these through in lit, and then some more to-dos here to probably just extract those slides on calling the Python and C APIs for interacting with these when you're not just using the command line tool and want to code it yourself directly. So yeah, there are a few other maybe like general workflow things that I'd like to get into these docs around, like if I have a safe tensors file from Hugging Face and I have a like Hugging Face URL with a model, how do I use that? Just like give a like concrete step-by-step walkthrough of that. So some of this may just be use case customer driven. Someone has a question, the answer can go up here and it can be a reference page. And yeah. Cool.
Yeah. Any questions?
Well, I'm going to ask the obvious one because Scott even pointed at it to do. The IREE parameter archive file, you know, can you say a bit more about the file format? How, what is it? I noticed quite a few comments in there that I found quite interesting. So, I thought I'd...
The file itself is so under is my screen share?
Yep.
So under IREE Schema's parameter archive, this is a standalone file, so it is possible to implement a parser just by pulling in this single file from the repo. It's a lot like a zip file, which is terrifying to say, but also like zip files were invented for a reason. Of you're spanning multiple storage volumes, and you want to be able to do things like substitute and erase files without having to go pull out your old floppy disk to update them and stuff. So it's a linked list of archive headers that exist in a single file. So you can concatenate these files if you want to do things like extend a file using an operating system primitive to quickly extend a file. You can do that and continue tacking on additional parameters to the file. That's most of what the header is, because we don't care about really anything about the actual content stored in it. The amount of metadata we track is very small. We do allow custom metadata blobs. So each entry in one of the files can contain metadata, but we don't specify what that is. But really what we store is the name of each entry, alignment requirements. This is important for when we're doing things like converting files, sharding files, joining files, to if individual entries in the file had certain alignment requirements, we can preserve those as we're doing conversion. And then we support several different types of entries. Today we support the splat entries, which are just inlined pattern values, big enough for complex of F64. And those at runtime, when they're loaded, will just be directly splatted into memory using a DMA fill, but contain really nothing on disk. And then we support data entries, and so those are inlined storage in the file, which really is just a range of bytes to some alignment. And then we have provisional support for external entries. I don't yet have this implemented in the loader code yet, but this allows you to create hierarchies of archive files. So you can have an archive that references other byte ranges in external files. So this would let you do things like create an overlay of, a safe tensors file that has, 100 gigs of parameters in it, and then 1 gig of file parameters in a different file, and you want them in a single kind of file that you can reference. So there's ways to kind of like also creating polyglot files. So you can have one file that is both a GGUF file and an IREE parameter archive by containing this header in it. If you want those things. So that's basically it. It's a linked list of structs, each one containing an entry. And And because we have a subset of the metadata that any of the other formats have, it makes it easy to convert into this format. Converting out of this format into other formats is harder because we don't know what a tensor is in here. We only know that each entry has some length to it. I guess the other features of it are it is segmented. So when doing updates, especially when doing extensions of files, you can replace and rewrite the metadata segment, for example, without having to move all of the contents of the data. And you can also have sparse files. So if you wanted to append a single entry to a file, those can end up in separate storage segments without having to completely overwrite the file. And then because of the alignment requirements in here and the fact that we're not tracking specific metadata about these, it allows us to, when it comes to writes of parameters, we have all the information we need to just directly do a write into the file at a byte range. So we don't need to worry about, like basically you can do in-place updates of parameter files from programs that are running, and treat these basically as like page file kind of like storage as you're actively running at runtime. So thinking of things like streaming LLMs and stuff like that, where you might want to actually page out transients, you can page them out to a parameter file here, treating it basically just as a slab of pageable memory. And that's basically the file on disk. So it's just a couple magic bytes and structs, but it closely mirrors what we have for our parameter index, which is our C kind of type for this. So when we load a GGUF file, a safe tensors file, or one of our own, we're just building one of these indices in memory, and you can see it kind of contains the same thing. So here's the pattern, if you have a pattern or a file reference, or if it's data, it just references the data. So this makes it really easy. Our entire parameter parser code is mostly just validation, range validation of tables and stuff, but the entire parser is 350 lines of code, most of which is validation. So it's real, which to be fair, so is GGUF. Well, not really. So GGUF, because it's non-hermetic, like these are the kind of things that have to be compiled in, and then there's also compiler defined. So depending on how you compiled GGML, that changes what structs are interpreted in what ways. So the GGUF one, this is the badness here that you need. You need this if someone goes and adds one of these. All the runtimes need to go add a new entry for one of these specific formats. But it's also a similar thing of its structs that you can splat into memory. Safe tensors is more complex because it's JSON, so we actually need to parse. There's a JSON parser in here to parse their metadata blobs, which is fun. So yeah, our format's really just designed to be structs in any language that you can get structs into. You can parse the files. Files are fully hermetic. There's no additional information that you need from the compiled artifacts to be able to fully manipulate them, which is how like IREE dump parameters and convert parameters and create parameters can work, is they don't need to know the details of the original program, especially as we start to think of things like tensors with encodings on them and stuff like that. None of the other formats have a way to really define the encodings beyond what GGUF does with its shady table of if-def structs. Whereas because we don't have to store that information, we don't even care. It's just how many bytes is it. So yeah, is that useful?
Yeah, thanks. That's really useful. Julian?
I missed some of the beginning, so sorry if you spoke to this, but for things like Benoit's usage of MMT4D and the way that the packing gets const-eval by the compiler, it's obviously a process that happens at compile time. You process all of those weights and write them to some format on disk. Can you use this mechanism to cache those results and reuse them later? And how does one go about doing that?
Yep, that's the intent. So it's not there yet, but the way that const-eval works is it's kind of like two big stages today. One, it identifies things that it can hoist into initializers. So it doesn't, and that's separable from actually evaluating those initializers. It's really just saying there's no dependencies on any input to a particular function to produce this value. And what is hoisted is something we decide. And so if one of the things that feeds into a particular computation is a device query, what is your L1 cache size? What is your vector width? What is, whatever, your exact architecture? Those can be hoisted into initializers. And so if you run that process, what you end up with then is a bunch of initializers initializing global values. And if what you start with is a bunch of parameters, those initializers are going to look like load the parameter, do some work on it, tiling, packing, transposing, whatever, or full computations, and then save back to a global the computed value. Const eval, when it runs, basically takes those initializers, puts them in their own module, and JITs it and runs them. It passes in the values and then gets the values out, and then it replaces the values with that, deletes the initializer, and it's just the baked global. So the thing we need to build is kind of the third step of that, which is for anything that is known at compile time. So any of those initializers that everything can be evaluated. Either you've specified fully your device configuration, so we can basically turn any device query into a constant value. Your SIMD vector width you specified, or you've specified a single device that only has one width, so we can fold that. That becomes constant. We can now const eval that at compile time. Or you gave us the parameter files, so you passed parameter files, and so we can do that. If we can't, so it is based on device configuration, we can't know, or it's based on parameters you didn't give us, then we can spit out a VMFB that is effectively what const eval is running today. So it's just those initializers. They get turned into functions. That is a VMFB with a function that is, evaluate or whatever. You would give it a parameter file as input and a parameter file as output, or potentially in place. But usually, if these change sizes, you don't want that. And you want to be able to rerun this if things change. User migrates data to a different device and it has different CPU parameters. You want to be able to run that. And if you overwrote your parameters, that's bad. So that module, and then on the runtime side, it's up to the hosting application to then say, at some point it decides whether that's app install time. If this is an APK, you get a notification of, deployment succeeded. You would go fetch your content and run this module. You could discard the original parameters if you wanted, if you can fetch them on demand again, or keep them. And then when you actually go to run the program now, as part of that outlining of everything, when we hoist into those initializers, the rest of the program is now assuming that those initializers are in a format it expects. So like if a pack got moved into an initializer, all of the rest of the program is assuming the data it has is packed. And so once we do that and you do this optimization, the parameter file you have on disk that you processed has the packed contents in it. You go to run your program, you give it those parameters, they're already packed, the program knows they're packed, and it just continues on using them. There could still be some things there. So if we, emit multiple variants of a particular dispatch for different architectures, like fat binary style, that's still something you'll want, because you'll have your VMFB that you've deployed or linked into your application statically, and it might, like we don't, parameters are separate from like going and deciding, can we prune a particular SPIR-V blob or function from it. But it'll work. So there will still be device queries, but it'll be device queries to decide which kernel to launch versus device queries to decide how to pack data, because that should have all been baked away initially. Modulo anything we couldn't hoist, so function inputs or outputs that we can't evaluate, those will still be done at runtime. There might still be packs and unpacks there for those reasons, but not on your parameters.
Well, this includes some mechanism to tell whether your cache parameters have been invalidated by some program or a compiler change, or is that all application developer to figure out?
Yeah, we have to pull the CUDA Vulkan kind of thing of like cache management is outside of our purview. So what an application that's tracking deployment of these things can decide, if it downloads a new VMFB, then it probably needs to invalidate its caches, because that VMFB might, have the architecture might have changed, the hyperparameter might have changed. Everything will need to be different. If the device characteristics change in a significant way, you didn't have a GPU before and now you do, or something. Especially if you just put these all on a thumb drive and copied them to a different machine and ran it. That's something that metadata that the application tracks in some application specific way will have to know. Likely you might want to even fetch a different model entirely, because thinking of things like when you fetch the model for the first time, it's like my device supports BF16. I will fetch a BF16 version of these parameters. What you don't want to do on an edge device like that is fetch an F32 and do an F32 to BF16 on device, because you've just wasted tons of bandwidth and storage space and stuff. So any application would likely want to be doing that kind of device determination anyway. And what you can say is, for my device, is a parameter file the same, and does it match the SHA of the file on disk or whatever, and is the model the same? And that's stuff we just don't know at the IREE level, but an application, if it's caching, doing over the air downloads of files and stuff, all that information should be there for it.
Yep. So more along the line, IREE would publish some guidelines on what would invalidate parameter caches, and then also at the application developer could build some mechanisms to regenerate parameters offline, like on server or whatever, and have at least some mechanism to validate that what's on device matches what we expect should be useful with the current VMFB.
Yeah, and one thing we can do, we don't yet, because there's a lot to do, but when we produce that kind of pre-processing module, there will be a function in it that is the go and do the thing, which loads all the parameters and saves them all and everything. We can also have a function in there that does basically any device query that is not just based on the input parameters. Like, we're not going to compute the SHA of the parameters you give us or something. You'll have to manage that. But if it's a device query, we know in the compiler what device properties can change, and we can manage that. So we could have a function that's basically, did anything change, of the queries that are actually made by the program. And so if something doesn't query anything, then that's great. And otherwise it would be there. And then what we can do is actually store that as a parameter itself and use that. So you can say, in this parameter file with these encoded parameters that are the device configuration, does it match? And that would just be something the compiler would spit out. The application could choose to query that as an optimization, but if it didn't and it just regenerated every time, then that's fine too. But features to avoid needing to do that if things change. But generally, Android does have callbacks and stuff like that you can get if you specify it in your manifest of like significant change to hardware kind of stuff for these cases. Games use that for like, if the GPU changes and it needs to re-download all of the compressed textures in a different format. So there's some things in there.
Awesome. Well, sounds like that'll be useful to a great number of scenarios.
Awesome. Well, we have 2-ish minutes before we're at time today. So anybody has a last couple of questions, or of course we can continue this discussion on Discord or on the mailing list.
There was one other thing that I can bring up. There's an email thread going on about setting retention policies on GitHub post-submit and pre-submit buckets. I just ran a little experiment downloading some files, looking at how large they are, and then seeing what those files could look like if we extract the parameters from them. And it looks like we're uploading and storing 130 gigabytes per benchmark run. For one of those files, it's a 400 megabyte MLIR file with embedded weights. Extracting those into parameters, I get a 300 kilobyte MLIR file and a 1.1 gigabyte parameter file. So I need to figure out why the parameter file is almost 3 times larger than the MLIR. But that parameter file could be shared across multiple benchmark runs and just kind of snapshot in a separate bucket. And then the individual benchmark runs could just pull the much smaller files, with the caveats we were discussing about performance, if there are transposes and packing and things that the compiler can't optimize yet. And the versioning thing of when is this data invalidated if multiple people are trying to use it at different versions.
Yeah, I would want us to, for benchmarks in particular, for correctness, it's different, but for benchmarks in particular, we'd need the ability to do the deploy time const eval, because they're just very sensitive to all the target information flags today. So we can't do that yet. But I think the bigger thing there is we're also, for some reason, storing all of the compile stats produced VMFB files, and that's just stupid. So you can half the size of that entire archive, but just not storing those. There's no reason to store those.
Yeah, like some of these
files, that's what we should do first before we do anything else.
Yeah, and I think your point about actually like the inliner import option one, I think at least gives us the storage saving while the same compile performance today. And I think also quite a few of these benchmarks would actually share the same data. So not even just different runs of the same one, but I recall seeing the same model, but with different
flags. Yep.
Yeah.
Yeah, that's where, if for benchmarks, we would want the const eval, because those flags are the load bearing parts of the changes there.
Okay.
Yeah, I've also been meaning to, thinking that we should have different test runners versus build runners, and the test runners should just have a squid proxy on them that, or something that keeps a persistent cache of artifacts, and basically then everything goes away. You can, and because you've got fewer test runners, if you do it right, you can make the disks big and all that stuff. So that's what we're doing on another org.
Okay, great.
Yeah, we should at least get rid of those compile stats files. There's no reason to keep, like, literally half of all the file size is just compile stats VMFBs. That's silly.
Yeah. We like our stats. Okay, awesome. Thanks, Scott. That was very useful.
Yeah, I'll follow up on the email thread for that.
Thank you, and thanks to you and Ben for presenting today, and for everybody who was joining. And we'll have our next meeting in a month. Feel free to send questions and topic suggestions. Yeah, thanks everyone.